Okay, good afternoon, everyone. To some people, welcome back. Welcome to the fourth edition today of the Week of Webinars. The Week of Webinars is part of the ECMWF Summer of Weather Code. And for those who don't know ECMWF, we are both a research institute and a numerical weather prediction organization. So we have a numerical weather prediction model running and provide weather forecasts to our member states and national weather services. And the ECMWF Summer of Weather Code is a collaborative online program that ran for the first time this year. And we basically invited developers, startups, scientists, and students to work with us during the summer on innovative weather-related software. So we had since May, 5 teams teamed up with ECMWF mentors, and one of those projects was developed by 52 North, mainly by Norwin Roosen, and was supervised by Mathis and Simon. And so I will hand over to Ruth to explain more about the motivation of the project. She was one of the mentors, and also Carlos, he also mentored the project on the technical side. Just a short about the structure of the webinar. We will have a presentation from Ruth about the motivation of the project, and Norwin will describe what they did, and then later on we open the floor for questions for anyone who is interested and has questions. Okay, so then I hand over to Ruth.
Hiya. So for those who don't know me, I am Ruth Coughlin. I'm a graduate trainee here in ECMWF, working on the environmental forecast team, and I'm one of the 3 mentors on the web crawler for environmental data. So in a bit, I'll be introducing the web crawler, the background, the motivation, and the concepts to it. And I'm one of the 3 mentors, so I'm involved due to the fact that I was responsible for the motivation and concept, and Carlos was on board to do with the fact it was technical expertise.
Yes, my name is Carlos. I should have been more involved with the technical bits, but I haven't done much, mainly because we have this tremendous help from Simon and Mathis from 52 North, who have basically taken a lot of the burden from the technical point of view. So perhaps, Simon, if you want to introduce yourself and explain the role of 52 North in this mentoring process, that would be great.
Okay, yes. So my name is Simon Jirka. I'm a team leader at 52 North. Perhaps a bit on the background. 52 North is a small company based in Münster. In Germany, we are basically working in the field of applied research for spatial data infrastructures and geoinformatics. So important topics that we have are sensor web technologies, web-based geoprocessing. And when we saw that program, the Summer of Weather Code, we saw some very interesting fits with our expertise. And so we wrote that proposal, and together with Mathis, we supervised Norwin, who did a lot of work, and I'm happy that Norwin now is able to present our results for this project.
Yeah, thanks. I'm Mathis Rieke, also for 52 North, as Simon introduced. I've been working with 52 North for the last more or less 10 years. I've started as a software engineer in my student years, and now I'm more or less a software architect and project lead. And supported Norwin in this project in technical questions and architecture approaches, which could be taken, and also in a general sense, like how can we make a good story out of that, and how can we make it use case driven, that it fits the overall goal for ECMWF. So I think that's more than enough for saying about me. I'm skipping over to Norwin.
Yeah. Thank you. I'm Norwin Roosen. I'm currently a master's student at the Institute for Geoinformatics in Münster, studying geoinformatics, and currently doing my internship at 52 Degree North. So this project was part of this internship, and so I had quite some time to devote for this project. And it was lots of fun, and I'm looking forward to present it. But first, Ruth will go into the details of the background.
So just to give you a little background behind the motivation, currently I am working on GLOFAST, which is the Global Flood Awareness System. So it's a hydrological service which provides global overviews of upcoming flood events. And in this system, there is no real-time hydrological data. So for us, that means we don't have data to process global hydrological forecasts, and we don't have regular global hydrological forecast verification. So in general, real-time hydrological data is actually freely available across the globe everywhere. But unfortunately, there's no central body managing the data acquisition, and there's no global data store of real-time hydrological data. So part of my role here in ECMWF is to incorporate this real-time data into the existing ECMW databases. But one of the problems is before I can put this real-time data into the databases, I need to know where I can find this data. So how do I find available data sources? Excellent. So I created a manual methodology which identifies URLs with time series data. So the way I did this is I had 30 keywords of hydrologically based, which I combined into various combinations. So these became keyword combinations. Then depending on country, I translated it into a country's official language. So for example, South Africa has 11 official languages. So these keyword combinations had to be translated into these 11 official languages. And from there, then these translated keyword combinations were put into a Google search engine and lists of URLs were generated. Then I had to go and manually annualize the returned URLs for viability. So viability means basically, was there any data that was any of use for me? And it meant that I had to go into each URL individually. So if I deemed one viable, then I extracted essential information, which is basically agency name, URL, contact details, and then I saved all this information so I could basically revisit it again for development of data acquisition programs. But there's problems with the manual methodology. So basically it's time consuming. So there's 195 countries. There is more than one official language for many of the countries. But also when you do Google search engines, you get so many lists of URLs, but you have to check all of them to see if they're viable or not. So it's a lot of work. And also you'd have to do it on a regular basis to keep up to date with all the resources that are coming online. So the manual methodology isn't feasible long term, so I needed to come up with another way of getting this data, and this is where the Summer of Weather Code comes in. So the concept is to develop a tool that undertakes the manual methodology. So this undertakes the manual methodology, but also is usable by a wider audience. So making a tool that uses keyword combinations that aren't just hydrology based, and also that is easy to run within the ECMWF computer infrastructure. So our overall goals for the tool would be to accept different keywords and combinations, to translate these into all national languages for a country, undertake automatic keyword combination searches, and the hard bit, automatically assessing and ranking these URL results, then extracting the information from the URL and presenting all of these in an easy-to-use format. And the last bit is just quickly the benefits to ECMWF. So the identification of more data sources means for us more data, which we can always use more of. And it's a keyword-based tool, so the changes in the keywords means that the tool can search for different data. So it can have a wide variety of uses across ECMWF, and other sections can find data that's of interest to them. And now I'm just going to hand over to Norwin.
Right. So let me describe the solution we came up with, because the approach was to look at Ruth's workflow, the manual workflow, and try see where we can automate things to speed up the process and maybe even make it more generic than to look at hydrological data. So the outline was, the goal was, as already described, to develop a tool to search the web systematically, to identify new data sources, and we came up with a solution that comprises of a whole application, which provides you with a search engine, but not the generic search engine as Google, but with a thematic focus. So you have a custom page rank showing data sets on top instead of results matching the keywords the best. For each page we fetch, we do a classification of the web page, whether it contains data or not, and do some metadata extraction in order to speed up the process of looking at each page. So useful data such as contact information and licensing information is extracted. Let's have a look at the challenges we face. There are mostly two challenges. One is that the web consists mostly of unstructured data, and it's thus really hard to analyze. So some data sets are provided on the web and increasingly more often in data catalogs, which are listing the data with machine-readable annotations, and they are easily accessible for discovery of new data. So this is not really our focus, but we are looking more on pages which are more old school and tend to have the data really hidden on the page. So there we encountered several different kinds of pages which are provided by agencies which provide data. This goes from data reports embedded in PDF pages, which is not really useful, to data points encoded in the HTML page, to hints that you have to request data via email or something. Sometimes you have web mapping applications which display the data interactively, but you don't get direct access to the APIs in the background providing the actual data. Right. The other challenge was to tackle the issue of the language, because we are looking for data with global coverage, and we have to effectively find all the data. We have to search in the local languages as well as in English language. So because this translation step is really time consuming, we have to remove these language barriers, and did this with automation of the translation of the search keywords as well as the page content that's on the page itself. Another issue is that the content identification, whether a page contains data or not, is difficult to do without knowledge about the language, because if you do it with keyword searches and so on, you are heavily dependent on the vocabulary, and this changes with each language. And this is basically the hardest issue, and yeah, I'll come back to that. So let's look at the features we implemented to solve these challenges. So basically we have a web search application, which is the hybrid approach of classic Google search, as well as custom crawling of the web pages provided by the Google search. So the idea is to translate the search terms automatically and submit them to Google, and then look at the results from Google and further do processing on them and look at the outlinks from each Google result. For each page, we do content analysis, meaning we classify the results, whether they contain data or not, with a custom machine learning model that we have trained, as well as the metadata extraction, as I already mentioned. The whole thing is managed through a web front end. So you start crawls and can stop them through the web UI, as well as have a result listing and result exploration visualization of the for the results, and so you can explore the resulting data. Right. So let's have a look at how it works. Here's an architecture diagram. it's I will walk you through this. Then it's quite simple. So it's basically a microservice-based architecture with several backend services, and the idea is to start a new job for each keyword you want to query, meaning that when you submit a keyword, we search this part of the web regarding this keyword and don't crawl the whole web, which saves a lot of bandwidth, time, and disk space. So it's really narrowed down on the keywords. Okay, so let's go through the process of creating a crawl and see how the processing is done. We start, the user faces only the web front end. And there there's an interface for a dialog to create a new crawl. There you have to enter keywords as well as the languages you want to have the keywords translated into. And this data, as well as some additional parameters or options, are submitted to the backend. And there's this controller which manages the crawls. So you can start a new crawl, stop a crawl, retrieve the results. And when starting a new crawl, it first takes the keywords and translates them. We are using an external translation API for this. This is from Azure, but you could technically plug in other APIs as well. And with these translated keywords, these are submitted to a search engine where we use Google Custom Search. And then we get back some starting points for the crawl. So these pages are already valuable, but we want to look at more pages. So we look at the links linking from this page. Right. So these URLs are then indexed into an Elasticsearch instance, which is regularly polled by the crawler application. The crawler is based on Storm, Apache Storm, which is a stream processing framework enabling a stream-based workflow. So as new pages are inserted into the Elasticsearch index, they are processed and coming out as they are done. So it's not unlike a batch process. You have a far more interactive workflow because it's essentially less latency. So in this crawler, you have a pipeline which fetches the pages and extracts outlinks. And these outlinks linking to other pages are then indexed directly back into the Elasticsearch index. So they go through the crawler pipeline in the next iteration. We do on each page we do a language identification, and after that, based on the language, we do a content classification, which determines whether it's likely that we have data in front of us or not. Additionally, we do some XPath queries on the HTML in order to try to identify which kind of page content we have in front of us. So whether it's an API, what kind of API, if it's real time or not, these kinds of questions. As well as there's additionally contact information is, for example, is also crawled, and all this metadata is then also indexed into Elasticsearch, into another index, which can then back to the front end be queried and visualized. We will see this soon. Additionally, there's a meta visualization which shows basically performance metrics of the crawler and the classifier. So this gives you an overview how the application is performing. Right. So, but instead of explaining this, I can just show it to you, I think. Here you should see my browser on the starting page of the application. We have 4 views, one showing the search results, one's showing the crawl list, and one providing a dialog to create a new crawl, as well as the mentioned metrics visualization. So what you see here are already results that were indexed by a previous crawl that I started. But I think it's best to start with creating a new crawl. So you can have a look at this. So starting a new crawl is a 3-step process. You enter keywords in the first step. So let's do an example crawl such as water level. And this is basically a keyword right now. And because we have synonyms for the same terms, which we can use to describe the concept we are looking for, we can add more keyword groups. So these are then submitted as separate Google searches, but are grouped into the same crawl, so it's easier to manage. So we could enter instead here something like river stream flow, and yeah, it submits an additional crawl. Below this, we have common keywords, which are keywords that are appended to each keyword group. So basically, it just spares you the effort of typing it into each keyword group. So we are looking in this case for real-time data. Right. So in the next step, we define the languages, because the crawler operates on languages only, but languages are not really a useful concept. So we provide an interface to select languages by country. So if you go for a country which is multilingual, such as Belgium, we can see it selects 3 languages, which are then provided, right? Adding Germany does not duplicate the language. Yeah, I think you get the idea. We can additionally search with the untranslated keywords in case we are looking for English pages. Yeah. In the last step, we just give the crawl job a name and provide can set some parameters. So let's call this Stream for Belgium, and yeah, the first parameter crawl depth defines basically the number of hops we do from the first Google results to the next linking page to the next linking page. So with this set to 1, we just fetch 1 outlink, but we could go for more. This provides us more results, but has the potential to provide more irrelevant results. The other parameter defines how many starting URLs we use for Google. So this is basically the first 3 pages, but we could go for more. But technically, this is kind of limited because we are using a free API key from Google, which provides us with 100 searches per day. So yeah, we are not quite unlimited here. The crawl stops automatically after a given number of minutes or a given number of results fetched. So this can be configured here as well. So when we launch this crawl now, in the background, the keywords are translated and sent to Google, and the resulting URLs are then indexed into Elasticsearch. Right, and we are redirected to the crawl list view, which gives an overview of the translated keywords, which basically gives you an idea of, lets you control this, the results of the translation. You can additionally click this button, which basically performs the same Google search that was submitted in the background. So yeah, you can control this as well, this is kind of different than doing it by hand, because it is automatically sets parameters such as page language and page location, further narrowing down the geographic boundary. Right, so we can see the crawler already started indexing new pages. We have 75 results already, and can view them now in the resulting list. Clicking on view results, I clicked it now on the previous scroll in English language, just to showcase it. We only have these results from this scroll now shown to us. Each result has a couple of action buttons, the title and host information, as well as some tags. And these tags identify what kind of data was identified by the crawler. Clicking on a result exposes the extracted metadata, which is kind of the language and the classification, which is in this case dataset with a confidence of 2, which is not a percentage but a scaleless value. And in this case we have identified a data API URL on this page. I think this describes the metadata of this API. Can look at it. Yeah, seems so. To open a page, you can use this link button. If this page was not in English, there would be additionally a translate button, which opens the page translated to English through Google Translate, which speeds up the process for foreign languages. The buttons on the top provide you with a manual classification interface, which allows you to label each page whether it contains data, is unrelated, or is related but not containing data. So this provides you with an interface to label more results in order to train a new classifier. Because the classifier that's now used is trained manually on, I think, 700 pages, and you can extend this for a broader fit. And additionally, you can train it for other languages. Right. If you are not happy with the results we have here, you could further do a full text search on top with some keywords. And actually, you can query all the metadata that was indexed as well, so such as language, such as the classification, confidence, and so on. There's clicking on the question mark button, you get a display of the available metadata fields. And I prepared a demo query, for example, which is now matching only results indexed as dataset and in the German language. This crawl does not provide any results in German, but if we remove the filter, which only selects crawls from this crawl, results from this crawl, we should get results. Okay, it's not working. Well, okay, now we only have pages in English, in German, from the crawl we just started. So we can still explore these pages and have a look at them. Additionally, we can now search for a given keyword. Which narrows down the results. We only have 6 results now, so I think you get the idea. The last view we have is the crawler metrics, which displays meta information such as the number of results per host, and we can have a look at the number of results per dataset crawl. So we have here roughly 53% identified of the results identified as dataset, and the remaining 45% identified as unrelated. So, and we can see in the other crawl it's kind of different. So this can be useful to assess how well the keywords we entered match actual pages containing data. Yeah, there are additional metrics such as confidence metrics showing the performance of the crawler. When we provide a manual classification on more results, this gets more meaningful. Right, and here we have a display of the crawl performance, which basically shows the throughput of pages per 30 seconds. But this is mostly useful for debugging and assessing the keywords that were used. Right. So that's basically it from the demo. Maybe I can do a short discussion whether closing the loop, whether we achieved our goals. So I think this application provides a quite effective interface for discovery of new websites and datasets, because it ranks the pages basically in a different way than a Google search would. And additionally, it kind of abstracts the language away from the search process, because you don't have to translate it manually. What's kind of difficult and not really solved is the classification for each language, because we use a machine learning classifier that's dependent on the language. We have to train it for each language, and in this project there was just the time to do it for the English language, and this kind of misses the goal to do a data set search on a global scale. Yeah, this we had to do. We decided to go with the language classifier, the machine learning classifier, because this worked far better than doing manual keyword searches, which were also dependent on the language. So it's still better than not doing it with the machine learning classifier, but you have this issue of having to train for a new training set for each language. For future work, I think this is the most important issue, to train more classifiers, so we can support better results for more languages. It's working without the classifier, but the results are not as well sorted, I think you could say. Yeah. Another point is we could look for more machine-readable schemas, which identify data sets by annotations. For example, Google just recently announced a dataset search, which is building on annotations based on schema.org, where you provide metadata for each dataset, which is easily machine-readable, and we could embed this in this content identification as well. Yeah, the last point is the crawler is not really optimized for performance, because yeah, we consider this a prototype, which is working quite well, but it's still a prototype. Yeah, so that's it basically. We provide the code Apache 2 licensed on GitHub. If you're interested in more information, there's the project wiki, which has quite some background information. And there was a blog post on the 52 Degree North blog, if you're interested in that. Yeah, thank you.
Okay, thank you, Norwin. Yeah, quite impressive what you developed the last 4 months. I would open the floor to questions. Are there any questions either on the weather room at ECMWF or online? I would be interested in what kind of features you used or for feeding the machine learning classifier.
Yeah, good question. I was absolutely new to machine learning, the whole topic of machine learning, and I had to explore this quite extensively. Yeah, the machine learning classifier basically extracts the text from the HTML page and does a back of words classification. Uses basically it splits splits the text up in each word, does some normalization on it using lemmatization, and then does some how it's called, inverse document frequency, and I lost the name, but once you have this vectorized representation, we're doing a two-class classification with a support vector machine.
Okay. And then we have another question. How difficult was it to find out if you had the right translation for each keyword?
Basically, I just trust Microsoft to do a good translation because we are using the cloud service from Azure, and we basically tested it a bit, and the results seemed quite good. And actually, even if it wasn't good, we didn't have a choice. So you have to go with the translations they provide you.
Okay, thank you. And another question, was there a particular reason why you trained separate models for each language?
Yeah, that's because of the approach of doing a model on the document of the word frequency in page. It's heavily dependent on the vocabulary you are using. And so this means each language has a different vocabulary, and it only works on the vocabulary used in this language. So you can feed the classifier that we trained with English data with Italian documents, but it will not really give meaningful results.
Mm-hmm. Okay, I think so far there are no further questions, unless in the weather room, Claudia?
No, no further questions.
Okay, so, oh, there's another question. How long does it take to train for one language?
Oh, I think on my laptop it was 30 minutes or something, which is quite reasonable. We used a training set of, I think, 600 data points for each class. So yeah.
Okay, it's not too bad. Okay, I think, yeah, that's it. So thanks a lot, Norwin, very impressive. Thank you, Ruth and Carlos, and also Matthias and Simon for being available at the webinar. And yeah, for those who will be interested, we will have tomorrow another webinar. It's about innovative visualizations, and it's at the same time at 4 p.m. British Summer Time. And yeah, we're looking forward to welcome you tomorrow as well. Bye, and thank you.
Thank you.
Thank you.
Bye.
Bye-bye.
Bye.
Hopefully.